welcome to another astronomy lecture. This time talking about the evolution and distribution of galaxies in the universe. Basically get into like the really big structures in the universe, bigger than galaxies, and how those things and galaxies have changed over the lifetime of the universe. Well, for one, I've told you that the collision and merger of galaxies seems to play an important role in how galaxies change over time. This is a pretty cool image of two galaxies that are merging, sometimes called the antenna galaxies. A little bit further away image on the left, a bit closer up, and in the image you can see the really bright spots, really bright yellow, kind of white spots are like the centers of those two galaxies. And some of the other stuff, I feel like there's really dark areas as there are dense clouds of dust and gas. But there's also the very bright pink and areas, and due to the collision of these galaxies and the gases, the interstellar medium of these galaxies getting twisted around and pressed together during this collision tends to trigger a lot of star formation. So the blue and pink bright areas are stars being born, or newly formed stars, which are still very bright, hot. I wanted to note, I don't know if I'll use this term that much, but to be clear, in astronomy when they talk about evolution of galaxies, it's not like evolution in biology where generation after generation there's changes. The evolution of galaxies is literally like how they change over the course of their lifetime. So another term for like the life cycle of a galaxy. I've mentioned this idea a couple of times before, but I want to try to emphasize it here because we're going to start thinking a lot about looking very far out into the universe. And when we do that, we're looking back in time to the early age of the universe. I told you about that before, but I'm trying to emphasize this here with somewhat of an analogy here. And that would be thinking about watching or experiencing a lightning strike. So if you ever see lightning, then you probably know that you typically will see the flash of the lightning, and then depending on how far away that lightning is, you'll hear it. You'll hear the thunder, or like the boom, crash of that lightning a few seconds later. So why is there that separation? Well, both sound and light take time to travel from the event, the lightning burst, the lightning strike, to you. So the sound just travels a lot slower than light. Light travels very, very fast. So the sound might take a few seconds to get to you, whereas the light takes like billionths of a second. But each of them takes some time to get from the event to you, from the actual lightning strike to you. So when you see the lightning strike, you're actually seeing an event that happened like just a short time ago. And then you hear it a few seconds later, you're hearing an event that happened a few seconds ago. Because light travels so fast on our normal day-to-day timescales and interactions in the world, we tend to just think of it as being instantaneous, right? Like you flip the light switch on, you immediately see the light. But in fact, the instant that light turns on, it takes some very short amount of time before the light travels and hits you in the eye. It's just so fast it seems like it's instantaneous. But we start to get more of a grip on this idea when we think about light traveling from the sun to the Earth. Right? That's a pretty substantial distance, one astronomical unit. And in fact, it takes light that leaves the surface of the sun about 8 minutes to get to Earth. What this means is, well, when you look at the sun, well, I wouldn't look directly at the sun, but when you see the sort of sunlight, what you're actually seeing is light that left the sun 8 minutes ago. So you're sort of seeing the sun 8 minutes in its past. And if you think about things even further out in the solar system, Neptune is far enough out that it takes roughly 4 hours for light that leaves the surface of the sun to reach Neptune. And so if you're on Neptune looking at the sun, you're seeing the sun 4 hours in its past. This just keeps going. The further and further out you look, the further and further into the past of an object you're sort of seeing. So like Andromeda, one of our neighboring galaxies, and it's about 2.5 million light years away, meaning that the light that you see from Andromeda, and you can see it in a reasonable telescope pretty easily, Even some phones, I think, are able to capture it all right these days. But that light that you see left Andromeda 2.5 million years ago. So you're seeing how it looked 2.5 million years into its past. Just one other example, we've looked at the elliptical galaxy M87 a number of times. M87 is about 50 million light years away, meaning the light that just gets to us now left it 50 million years ago. So we're seeing well into its past. And it just keeps going. You look at something that's like 1 billion light years away, that's light that left it 1 billion years ago, so you're seeing way into its past. So this is why when we look very, very far out into the universe, what we're seeing is light that left these very distant objects a long time ago, billions of years ago. So our current estimate for the age of the universe is about 13.8 billion years old. And so if we think about looking really far out into the universe, we can also think about that as looking at a certain amount of time after the beginning of the universe, or after the time the universe began. So you look out 10 billion light years, you're seeing light that left an object 10 billion years ago. That was when the universe was about 3.8 billion years old. Or if you look out 13 billion light years, you see an object that's that far away, then you're seeing an object in the universe as it was when the universe was less than 1 billion years old. So what are some things that we see or notice if we look out at things really, really far away? Right? So very early on in the history of the universe. Well, even within a few 100 million years after the universe began, there already seem to be smallish sort of galaxies that have formed. So it seems that galaxy formation didn't take all that long to get going. Right? A few 100 million years. Most of those galaxies that we see are fairly blue, just spectrally, so that sort of indicates that they're made up of very hot and bright stars, typically pretty young stars. It also just kind of telling us there's a lot of star formation happening. Kind of makes sense early on. Looking 13 billion light years away, trying to look at an object that far away, quite difficult. Right? You don't get a whole lot of light from it, it's so far away. So doing like full spectroscopy or looking at spectral signatures from these objects that are that far away can be quite difficult, even still, or even today. However, we have managed to find some objects that are incredibly bright, meaning that they're putting off a lot of light. And so even though they're that far away, we still do manage to get enough light from them to analyze the spectra coming. Be able to like spread out that light and look for those spectral lines. And what do we see? Well, even within a few 100 million years, we see spectral signatures for heavier elements than just hydrogen or helium. Things like carbon and silicon. And if you recall, making heavier elements is a process that stars do, right? Throughout their lifetime, they'll fuse lighter elements together to make heavier elements. Hydrogen to helium, helium to carbon, oxygen, so forth. So if we look really, really far away, really early on in the history of the universe, and we still see some of these heavier elements, it's telling us that even before that, even earlier on, stars were already forming and going through whole life cycles and blowing up and seeding the early universe with these heavier elements. And some of the things that help us look very, very far away are what I told you about last time, active galactic nuclei. It's like quasars that are incredibly bright, so give off enough light where we can actually see them decently well. So here we have some images of galaxies that are very far away. Both of the large images maybe are from Hubble's deep field imaging, but on the left there's like a closer up image where the arrow is pointing for Hubble, where you can see this kind of faint little blob, very, very distant galaxy. And then below that is Spitzer, which is, I think, maybe X-ray? I'm not remembering right now, but it looks even more fuzzy, but there is still a source in the center. This galaxy is something like 13.2 billion light years away. So we're seeing an object very early on in the history of the universe. And in fact, we were able to detect the spectral signature of hydrogen, which is typically produced where there's a lot of star formation. So we see a galaxy very, very far away very early on in the universe, and it's already forming stars. The image on the right here is a bit closer, still pretty early on in the universe's lifetime, but about 11 billion light years away, so a couple billion years after the start of the universe. And this is a group of galaxies that were measured. They're all pretty small, saying about 2,000 light years typically across. I remember, the Milky Way is maybe on the larger side of galaxies, but it's 50 times that, 100,000 light years across. So this is pretty typical. You see early on in the universe, the galaxies are generally still much smaller. There's also pointing out that all of these galaxies are in a fairly close region to each other, which means they're probably on their way to colliding into each other. So a lot of stuff changed about our understanding of the universe in the last 100 years or so. It was like Hubble in like the 20s pretty much convinced everybody, at least in the scientific community, that there are galaxies beyond our own, and technology was advancing so we could see these galaxies a bit better. The thing is that for a while, it still wasn't possible to see further than like several billion light years away. It didn't really resolve much. And so all the stuff that we saw for a long time, or for a few decades at least, was stuff that was around since like the second half of the universe, or maybe even a bit later than that. But Hubble made his classification system based on those kinds of galaxies, right? There were like the spiral, and the elliptical, and the irregular galaxies. And for a while it seemed like the universe probably just produces those, and that's kind of what there is. That wasn't until we were able to make instruments that could let us see even further away. And when you look back earlier on in the universe, it turns out that Hubble's whole classification scheme doesn't even really work, right? There's not really any sort of distinct spiral, elliptical kind of galaxies earlier on. They're mostly just kind of like smaller, clumpier kinds of things. So for instance, if you look back or look out like some 10 billion years, or when the universe was like a little over 3 billion years old, there are hardly any galaxies that are more than like 10 billion times the mass of the Sun, and this is still 200 times smaller than our galaxy. Fairly small. And as I mentioned before, nearly all of them are rather blue, it's indicating that there's a lot of star formation going on. If you go back even further, when the universe is about 2 billion years old, you generally see like even smaller kinds of galaxies, and there seems to be a good bit of like seeds of later galaxies. So just sort of like smaller, clumpish things that we think through like collisions and mergers with other galaxies around it might build up into larger and larger, maybe elliptical galaxies, or possibly build up into spiral galaxies. But those seeds are sort of like the cores, it seems, of later, larger galaxies, or galaxies like we think of them now, or that exist generally now. Here's some more images of pretty distant galaxies that seem to be going through a lot of collisions, mergers. There's a grouping, or like a cluster of galaxies, is about 8 billion light years away. So when the universe was maybe like 5 billion years old, something like that. And yeah, there's a bunch of galaxies, something like 80 galaxies in this cluster, and it's like at least 13 are results of mergers, collisions. So the whole grouping is kind of shown on the left there, but closer up images of some of the individual galaxies that seem to have experienced collisions are shown on the right here. These different ones. So you can kind of make out like there's like bright centers to the individual galaxies in a lot of these, and there are different kind of stages of swirling around each other and interacting, colliding, as we call it. There's some more examples of galaxy mergers. The top three, actually, A, B, and C, are all images of the same collision, and then a close-up of one of them. In A, just like a high contrast sort of black and white image, and you mostly can make out sort of the center of the galaxies. And then in B is a radio image, and so the stuff that you're mostly seeing is the cool interstellar gas, probably the 21 centimeter line from hydrogen, I told you about a while ago. But yeah, we see sort of the distribution of the cooler gas in both these galaxies, and you can imagine, one kind of gone through each other maybe, or passed by each other. They're probably going to keep wrapping around. The last image on the top is, I believe, of a smaller galaxy in that merger, so like the one on the top in the first two images. And it seems that the red sort of gas that's being pushed out of this galaxy is probably due to supernovas. So during that time that their galaxies are passing by each other, there's a lot of star formation that's triggered. It's some very, very massive stars that are formed, and so within 10 million years, 100 million years, those very massive stars are going to go supernova. We're probably at that point where a lot of those stars have formed at some point during a collision, further apart, and a lot of this supernova happening, spewing out stuff from the galaxy. Then down the bottom, a few other images, all, I believe, in the visible range, probably from Hubble. The bottom left, D, probably a larger spiral galaxy that interacted or collided with a smaller one and just kind of stretched it out. E is a couple of spiral galaxies probably interacting. F is kind of an interesting one where it seems to be that galaxies are sort of passing through each other and pass through in the right way, where one sort of created like a ripple effect in the other one, and that ripple compresses like gas as it goes through the other galaxy and triggers a bunch of star formation. And so you get this very interesting looking image where you have this like ripple going through the other galaxy, a bunch of stars forming. Pretty cool stuff. So hopefully you're getting the picture by now that galaxies merging, colliding, I think is pretty important in how they've evolved over time, how they've changed over time. They started out in the very early universe, smaller galaxies started to form pretty quickly, but in order to build up to the bigger spiral and elliptical galaxies we see today, I think there's a lot of colliding and merging going on. Here we have some computer simulations showing what a merger of two galaxies might look like. On the left, just sort of a time lapse where it seems like maybe a bigger and a smaller galaxy kind of collide together. Sometimes when one of the galaxies is much bigger in the merger, astronomers call it galactic cannibalism. Seems a little bit much to me. But anyway, this might be an example of one on the left. And they kind of swirl around each other, and those two eventually end up as like probably what we call an elliptical galaxy. And there's a fairly similar process going on in the animation on the right here. And keep in mind, this process takes at least like 1 billion years. So before sort of settle down into a new stage, at least like 1 billion, maybe a couple billion years. Oh yeah, also on the left, the blue areas are indicating a lot of star formation that happens because of this merger. So a lot of star formation happens, but eventually towards the end, or when it starts to settle down again, not much star formation anymore, or not as much. One other interesting term about mergers is what we call starburst galaxies. And as the name implies, it's like bursts of star formation. Let's see, on the left, we have Stephan's quintet, which is actually only the 3 yellowish galaxies that are close together, that are really gravitationally bound. I think the other one in the upper left is actually a decent ways further away. It's not really part of that cluster. They sort of look like they are. But the ones that are in the cluster are interacting and are in the process of sort of colliding. And you can see like bits of blue and pink that are due to a lot of star formation happening. Similarly, in the second and the third image here, these we believe are galaxies that are in the process of colliding, and due to that are forming stars at a much higher rate than normally is the case for galaxies. At least, in the more recent past of the universe. As I've said, early on in the universe, it seems like there's a lot of star formation happening. But since maybe like the second half, or halfway-ish, maybe like 6-7 billion years, star formation overall has kind of fallen off in the universe, even still start forming. But when galaxies collide, even in the kind of current universe, they can bump up the rate of star formation like 10 or 1,000 times greater than average. So that's when we call these starburst galaxies. So that was all a bit about what we might call the evolution of galaxies. Sort of early on, smallish star formation, and then merging to become larger and form sort of the galaxies we see today. Now we're going to think about the distribution of these galaxies throughout the universe, and then in the end come to put these two thought processes together to get sort of a picture of like how the universe got from the very beginning to sort of where we are now. So similarly to like how somebody might go about making a map of their town, their city, their country, planet, generally start by working out where things are in relation to you, usually stuff close by, and then try to start working your way out, right? Larger and larger. So we've talked about the stuff around us a good bit, right? We talked about the Milky Way and where we are, where our solar system is. In relation to the spiral galaxy, there's the Milky Way. And I mentioned a few times, we have like our neighboring galaxies. We have a couple of small satellite galaxies around the Milky Way. When we start to think further out, like our sort of local galactic neighborhood, what we found, nearby at least, is that there are like a few dozen galaxies in what we might consider our local neighborhood. And astronomers have given this group a very inventive name called the local group. So the local group is basically the Milky Way, Andromeda, and there's a couple other larger ones, but the Milky Way and Andromeda pretty much make up a large portion of the mass of the local group. Right, about half of the mass of the local group is all just our galaxy and Andromeda. In terms of numbers, there's a lot more smaller, like irregular and dwarf elliptical galaxies. This is an attempt to look at or think about the local group. Generally put our galaxy at the center, and Andromeda is a bit of the ways off the disk and kind of up above the plane of the disk. It's another fairly large galaxy that's a decent ways past Andromeda, but closer to the plane of the galaxy. And then all kinds of other little galaxies in there. So this is like our local galactic neighborhood. And roughly 10 million light years across. So when we talk about groupings of galaxies, like, I don't know, it's not all that important to us, but astronomers use the term group usually to refer to like somewhat smaller collections of galaxies, maybe a few dozen, and then use cluster to generally refer to larger collections of galaxies, like thousands to even like tens of thousands of galaxies. For us, maybe we say group or cluster, it doesn't really matter. It's a collection of galaxies. That said, here's some pictures of some clusters of galaxies, groupings of galaxies that are relatively nearby us. On the left is the Virgo cluster, which includes our favorite M87 elliptical galaxy. The Virgo cluster says about 1,500 galaxies overall, and it's about 50 million light years away from us. So 50 million, that's like 20 times as far as Andromeda is. The other cluster here is known as the Coma cluster. This one's a bit further away, 320 million light years away from us. So we have our solar system, right? Our solar system's within the galaxy, Milky Way galaxy for us. Galaxies might have a few neighboring galaxies around them, maybe a few dozen, maybe even up to a few thousand. And we start to have these like clusters of galaxies. And something interesting that starts to happen when we look out further and further, particularly when we look sort of near or past these clusters of galaxies, even near just like single massive galaxies, is that there's like so much mass overall in this volume of space that, as I told you when we were talking about general relativity and space-time, that mass warps the space around it. And so when we look at stuff maybe like behind a cluster of galaxies, the light that's coming from behind it will sort of bend and warp around. And I mentioned this process before called gravitational lensing. These big clusters of galaxies can sort of act like giant lenses in the universe that are warping the light from stuff behind it. So the diagram on the top shows a very simplified version of this, where you have, us on Earth and some kind of massive galaxy in between us and a very distant quasar. That quasar is putting out a whole bunch of light, and when that light goes near the galaxy, right? The galaxy is warping space-time, and so the light bends and follows that warped path. You can imagine like two sort of light rays leaving this quasar, but they both get warped in such a way that they both end up coming back and pointing and hitting Earth. And so what does that look like to us? Well, we'll actually see it as if there was light from two different objects that's coming straight to us. So one thing that you have with gravitational lensing is you can actually get multiple images of the same object. And the picture down here is an example of that, where there's this galaxy that's in between us and a supernova that happened. That supernova is very far away, 9 billion light years away. The galaxy's like 5 billion light years away, but it's in between us and the supernova. So the supernova gets really bright, light comes off here, and that light sort of bends around the galaxy in such a way where we end up seeing multiple images of this supernova. 4 very distinct images being created by this gravitational lensing. So this lensing can be due to, like I said, just a massive galaxy clusters, but also, since it's just due to warping of space-time, and that's due to massive objects or a lot of mass, this can also be due to dark matter, or what we think of as dark matter. So it's stuff that has mass, it's matter, but it doesn't give off any electromagnetic radiation. So we don't see it. We call it non-luminous. Here we just have some visuals of how this lensing sort of happens. On the left is an animation that's sort of comparing light from an object that's behind a galaxy, and it's moving behind a galaxy. And on the very left there is like you imagine that you move the galaxy and all the mass with it, and so there's no lensing that happens. Right? That's just the object passing by. But if you do have the mass still there, the right-hand side of this animation, that mass is going to act like a lens to this light coming from the galaxy, and you get these warped images of it stretched out. I tried to show an example of this myself using just like a glass. So light also bends or refracts as it goes through different materials, and you can see a similar effect like if you try to look at something through like the bottom of a cup. So in the image there, it's like just some dots and such that are sort of like galaxies. You notice as they go behind the cup, whereas that lens kind of passes in front of them, to get these really warped images of them. But it can be very useful because like the way that the warping happens actually tells you about the stuff that's in between. So we can find out more about the galaxy clusters that are doing warping, and even like the distribution of the dark matter that's also in that cluster too. It's from the way this lensing happens. Here's just another image of this lensing happening, where we're looking at a cluster of galaxies, sometimes called Pandora's cluster. I think the galaxies of that cluster are mostly like these bright blobs, whitish like yellow blobs that you see. And there's a lot of other galaxies in the background, but some of those galaxies behind you can see are like fairly blue, and they've been, you can almost tell they've been like stretched out, where you start to see similar features like in the animation that you just saw, right? Where the galaxy might look like this, but there's this sort of lens, this matter lens in front of it, such that it's now been like warped and spread out. Now, like I said, the amount of lensing, or the amount of like warping of the stuff in the background, can tell us about what's doing that warping or how much matter is there. And this is actually another place where we find evidence of dark matter, other matter that we just can't see, but it does gravitationally affect what's around it, warp space-time. So we try to see, or we can try to like estimate how much mass is in that region in order to cause the amount of warping that we see, the amount of lensing that we see. Pretty much always comes out to be a lot more mass than we can actually see there, a lot more than just the luminous mass. right? Those galaxies that are giving off electromagnetic radiation of one kind or another. It's another interesting image of some gravitational lensing happening and allowing us to see one of the furthest and faintest objects, galaxies, you've ever observed. And that's because just like a regular lens that you might think of, like a lens in like a telescope or like a camera, not only can it bend or sort of warp the path of light and make objects look funny, in the right circumstances, it can amplify the light from that image or the light from that object. That lensing can be in just the right way to sort of converge more of that light from the object. So instead of all this light spreading out, there's a lot of mass, a lot of matter in the way, and it bends some of the light in such a way that it sort of condenses it. And we get a better image or more light coming from this object than we would have if there wasn't any gravitational lensing happening. So that happened with this one in such a way where the galaxy is actually significantly brighter and larger than it would have been without the stuff in between. So it allows us to see it at all, really. This galaxy is very early on in the history of the universe, only 500 million years after the beginning. And like I've been telling you, these galaxies very early on are rather small. This one is only 850 light years across, 500 times smaller than the Milky Way galaxy. So there are clusters of galaxies. We've certainly seen that. The galaxies tend to cluster together. Go further and further along, right, back in that sort of map-making process, looking further and further out at larger and larger scales, are there even bigger sort of structures that seem to form the universe? And the answer is yes. It seems to be that clusters of galaxies tend to want to group together, right? Clusters of clusters, and form what we now call superclusters. These superclusters can be, like hundreds of galaxy clusters put together, which ends up being something like hundreds of thousands of galaxies altogether. Like a lot of stuff we've talked about recently, this is sort of still an active area of astronomy and sort of evolving thing. And so for a while, and until fairly recently, astronomers categorized the cluster that we were in, or the supercluster that we were in, I believe as the Virgo supercluster. But less than like a decade ago, I guess, reevaluated and decided that that supercluster, is actually connected to other ones. So at that time, the astronomers decided to name this supercluster formation that we're a part of, the Milky Way is a part of, Laniakea. This is one visualization of our supercluster, and the local group is indicated on there. Or the local group is basically just like us and Andromeda, one or two other fairly large galaxies and a bunch of smaller galaxies within about 10 million light years. Here now, we have this supercluster that we're a part of, which is something like 500 million light years across. And again, like over 100,000 galaxies in this structure. Pretty big stuff. These superclusters now are some of the biggest things that we categorize in the universe. 500 million light years across, incredibly large structures. And what do these structures sort of look like, or what's their sort of general shape? They tend to form into like filament sort of things, relatively like thin sheets, kind of ragged thin sheets. So you think of like paper that's been ripped apart. So the thin part, relatively thin, is maybe like 10 to 20 million light years thick. But in the other directions, these are 10 times as large, right? 100 million light years in the other directions. So it's fairly thin, but it's longer in length and width. And one of the other very large-scale structures in the universe, you could say, are the areas, the volumes in between these filaments, these superclusters, right? And that's what we just call voids. So these voids, it's not necessarily like totally empty of stuff. It's just much lower amounts of stuff than are in these filaments that make up the superclusters. But still fairly empty overall and very large, right? 150 million light years across on average. So when you look at this image, our local, or our supercluster, is sort of in the middle. It's like there's still some of a crossover of terminology, because they're still referring to it as the Virgo supercluster here, but that's only part of Laniakea. So, sort of middle, central area in this region is our local supercluster, and then there's these other superclusters around, and it's not necessarily easy to see what the structure is like from the image, but it's actually kind of like sponge-like. Right? Like there are these areas, these volumes that are like fairly thin but stretch in long ways in the other directions that are the superclusters, and then there are these sort of like open areas in between those superclusters. They're sponge-like. So talking about sort of like the big scale stuff in the universe, I wanted to show you probably one of the most ambitious mapping projects that humans have done, which is to map out the universe, galaxies and quasars mostly. And so there's this project that has been going on since 2000 called the Sloan Digital Sky Survey, and it's been a number of phases that have gone on. The video I'll show you here in a second was released after sort of the most recent phase of the project. The video was put out in 2020, and you can already see there these two kind of like fan-looking things, and hopefully you'll see, but I wanted to note that all the dots in those fans, those colored fans, are galaxies. And sort of the center of those two fans is us in the Milky Way. Just so you're not wondering too much, the reason that we have like these two shapes to the side like this is because you can't see very well through the Milky Way, the disk of the Milky Way, and so that area is still pretty dark, right? So that's the area sort of in between these fans. These are looking out of the Milky Way, or out of the plane of the Milky Way. A quick sort of zoom out. Galaxies and galaxies. There's something like 2 million galaxies and quasars that have been mapped by this project at this point. So here we start like on the surface of the Earth, and you see the constellations in the background, and we're going to just start zooming out, faster than the speed of light. You see the sun going down, and then pretty quickly get far enough where we're going to pass the stars that make up the constellations. So these constellations don't really mean much anymore because we're outside of that. Keep going out, eventually you start to see sort of like the disk of the galaxy. Keep going out. I'm not sure offhand what the red dots are supposed to represent. Doesn't matter that much. We're just kind of like getting a picture here. Zooming out from the galaxy. You can get far enough away. It's a pretty good smattering of other galaxies, more galaxies, more galaxies, more galaxies. And you can even almost see, while zooming out, these galaxies tend to kind of cluster into these filament-like things. And then we go all the way back in. And there we are again. Just a little ride through the universe. So a question that people had, and still are wondering, is why the universe looks like this, right? Why do the galaxies clump together? Why do they form these sponge-like structures? Why are there these big voids? But also why, you can see almost here, when you zoom out far enough, things are pretty evenly distributed too. So I think in the next lecture we'll talk about what we call the Big Bang and ideas of like how the universe got going to get to where it is now. I'll say a few more things here. And one point that I've emphasized before, say again, that there's still a lot of stuff that we know we don't know about. I've mentioned and told you about dark matter a number of times, and I told you about some of the evidence for it, like with the rotation curves of galaxies, or how fast stuff is moving from the edges of galaxies. It seems to imply that there's much more matter there than we can see. I also showed you in this lecture about gravitational lensing, and we estimate how much matter is causing that lensing. Again, we find that it's much more mass, much more matter than we see, that is luminous. In general, large scales at least, seems to be like 20 times more dark matter than regular matter. As if that wasn't enough, there's more. I told you briefly when we were talking about galaxies and about the expansion of the universe, expansion of space-time. I told you that, on a really large scale, space seems to be expanding. Right? The space in between galaxies, in between clusters of galaxies, is expanding. And I also mentioned that not only is that space expanding, the rate that is expanding seems to be increasing. Another way of saying that expansion is accelerating. It's getting faster and faster. And this is rather odd because if we imagine that there's only matter that makes up the universe, basically sort of the regular matter, protons, electrons, neutrons, stuff we're made up of, but also even dark matter, right? Stuff that we can't see. It doesn't emit any electromagnetic radiation, but it does interact gravitationally, does create gravitational attraction between other matter. If that was all the stuff that was there, then it doesn't make sense for everything to be pushing apart faster. Because what gravity does is it wants to pull mass together. And so even though stuff might be flying apart from each other, it's still being pulled or being sort of tugged on by all the other matter in the universe. And so we would expect that that tugging would want to slow down that expansion and eventually start to bring things together. So if anything, you would think that the expansion of the universe would be slowing down. It's not. It's accelerating. How do we come to terms with that? Or what do we think about that these days? Well, it's very mysterious to say the least. One way that we try to make sense of that, or at least think about what is causing that, is to imagine that there's some sort of stuff that presses outward. Somehow it seems to press matter apart. And one way to think about what this stuff is, or what it's doing at least, is it seems to act almost like the pressure of a gas. So in the animation here, very simple cartoonish animation of a gas that's inside of like a piston, and that piston has a weight on top of it. So why isn't that weight just pressing down and squishing everything? Well, that gas is just made up of atoms and molecules that are bouncing around, zooming around to make up that gas, right? And the pressure of that gas is actually just those atoms and molecules that are running into all the walls and running into the top and basically keeping that piston from pushing down. So the pressure of this gas, the pressure that's pushing against the weight, is really due to the energy of all the atoms and molecules in that gas. If you remember when we're talking about energy, this is like an energy of motion. We call it kinetic energy. So in a way, you can think about the pressure of this gas pushing against the weight as like the energy of that gas. And if it's more energetic, it's going to push more, and it might push that weight even up and away. So and that is like a fairly simplified explanation of what it is, this thing that we call dark energy. So what seems to be happening is on very large scales, there's something that's pressing matter apart. So it's sort of like a pressure, but that pressure we associate with an energy. Since we don't know anything about it really, we hardly know anything about it, we call it dark energy. Still very mysterious. And now, so finally, we can kind of think about how the universe has evolved over time. So we have some idea of how galaxies evolve, how they change over time. We have more and more detailed maps of how galaxies are distributed. And even though we don't know much about it, we know some stuff about what we call dark matter and dark energy. And so try to put all that information together and make a coherent picture of where the universe started and how it got to where it is today, given all these different pieces. And we'll talk more about this process, at least the beginning of this process, in the next lecture. But to say right now, overall picture is that the very early universe, right, everything was much closer together, much more dense and energetic, but also pretty smooth. You go smooth, like everything's fairly uniformly distributed. You say fairly smooth. There's like tiny little variations in what otherwise like very evenly distributed stuff in the very early universe. And that being, matter and dark matter. But then as the universe expands, this stuff spreads out more and more, and those tiny little variations in what was otherwise a smooth very beginning start to form into more and more clumpy areas, right? And what start to become these very early galaxies, first couple billion years. So we go from a very smooth kind of beginning, a couple billion years later, things are clumping together a bit, and we're getting some smallish galaxies. And then the smallish galaxies are going to be colliding too and starting to build up to larger galaxies. Billions of years later becomes sort of present time, or how the present structure looks, where we have up to these fairly large structures, these like filaments or these superclusters of galaxies. So yeah, sort of like sponge-like, also kind of like web, almost like web-looking in a way. And this large-scale picture is sometimes referred to as cosmic web. And the last thing I'm going to show you then for this lecture is that process I was telling you about, but as a video, like an animation, starting out with like fairly smooth, evenly distributed stuff in the early universe, and then as the universe evolves, you see stuff start to come together and form galaxies. Those galaxies come together to be like groups of larger galaxies. Those continue to clump together to form superclusters. They're like filament kind of like structures, web, sponge-like looking structure overall, and eventually to get to sort of the universe that we see today, right? At least the universe isn't near us. If you look far enough away, looking back in time, so earlier universe. This nice, fuzzy, smooth distribution, but slowly, the tiny little variations in that smoothness are places where matter, regular matter and dark matter start to come together, form galaxies, and those galaxies can be fairly small to begin with, but if they're anywhere near each other, then gravity is going to want to pull them together, so they start to collide and merge, form even larger galaxies. Like on the right there, it's a fairly large merger going on to form a pretty large galaxy, but also plenty of smaller galaxies still around. The kind of structure, it's kind of wild, I don't know, nature, the universe, I guess, and repeat itself. Kind of looks like a sponge or even like this mold, maybe even like neurons. So we're well into the second half of the life of the universe now, and kind of getting to a place where things are starting to look pretty similar to how they do now. stuff and sort of clumped together to form galaxies and clusters and superclusters. That's not over, it's going to keep going. Well, that's it for this lecture. Like I said, next time we'll talk about the very beginning of the universe, and pretty close to being done with the semester, so exciting times. Have a good one, and I will see you next time.